Section 3, Bedload Transport Quantification. I'm Taka Mizuyama of Kyoto University. We have two speakers. We'd like to invite the first speaker, Damia. Would you start that?
Well, thank you very much. First of all, I would like to say thank you for the organizing committee for inviting us to do the chapter and also this talk. I apologize for being late in submitting some of the draft and some of the reviews, but at the end, everything comes together. I would like to say also that Joe Wheaton is around here. I will be leading now this presentation, but then maybe he will jump into the discussion if it's necessary. Finally, some of the results that we will present here in this talk are the results of different projects in which many people have been working. So I would like to say thank you to everyone that has participated in the different projects. What we will do in our talk is we will try to talk about the morphological approach to estimate sediment flux in gravel bed rivers, and also how high-resolution topography can be used for a better understanding of these sediment fluxes. We will mainly talk a little bit about high-resolution topography. We don't want to show a lot of pictures of nice things. We want to go a step further. We will try to go a step further. We will talk a little bit about the basics of the morphological approach, just to introduce this approach. And then we will move on to how we can use high-resolution topography to apply the morphological approach. And finally, we will list a series of challenges and open discussions we can discuss these days hopefully during the workshop. The talk has an outline of 5 different chapters. The first one is related to the high-resolution topography, as I already said. The second one is related to some principles of the morphological approach. In the third one, we will link the high-resolution topography with the morphological approach, how we can use high-resolution topography to apply the morphological approach based on 2 different approaches, the sediment budgeting and the path length. We will review this very quickly later on. And we will show the application of high-resolution topography using the data set from the river. And finally, as I said, some remaining challenges and opportunities. Let's talk a little bit about high-resolution topography. We were discussing with Joe a lot if we need to present the definition of high-resolution topography, but at the end we believe that probably it is necessary just very quickly. And we use the definition by Pasalacqua and colleagues in 2015, in which they say that we can consider high-resolution topography a data set consisting with different points with a location, x, y, in a Cartesian coordinate system, and each point has an elevation linked to this location. Of course, all together is what would comprise a point cloud. And they say that the minimum spatial resolution of this data set has to be 1 point per square meter. And of course, there's a lot of discussion on that because this will depend on the landscape that we want to characterize. There's a lot of ways to get high-resolution topography, and these ways have evolved in the time, and they are evolving a lot very quickly. We can use different methods. We can use methods based on remote sensing and aerial surveys like LiDAR, aerial photogrammetry, and also structure from motion. You will see a lot of examples of structure from motion in this presentation. And also we can get high-resolution topography using ground-based total station surveys, high-density GPS, RTK GPS surveys, and also, as you know very well, terrestrial laser scanning. And finally, in the wet channels, in the parts of the channels that are under the water, we can use boat-based bathymetry surveys. They can be multi-beam sonars, or they can be single-beam ADCPs, and so on and so forth. I will not get to the technology, I will not get to the nice pictures, but of course, what we want to remark here is that technology has improved a lot, has evolved a lot, and now there's many options of acquiring high-resolution topography. But having said that, there are 2 points that we want to just leave on the table that hopefully will prompt some discussion. Gravel bed rivers are very complex. Some of the rivers have vegetation. Other rivers have a lot of, the wet channel occupies a lot of the floodplain. We have different grain size distributions, etc., etc. And this implies that sometimes we need to combine different techniques, different technologies to get this high-resolution topography of the entire system that we want to characterize. So these are 2 examples that they are very contrast examples. This, for example, is the River, a ridered shallow river, in which the wet channel just occupies a small part of the floodplain. But we can move to other gravel rivers, that, for example, the Cinca River in the Spanish Pyrenees, in which the wet channel can occupy a lot of the floodplain. So therefore, here we have to combine different methods to get a continuous map of the surface that we want to characterize. Staying in the Cinca, this is a structure formation-based point cloud, just upstream from this site. And when you look at the point cloud, it looks very nice. For sure, we have 1 point per square meter, so we are in a high-resolution topography data set. But when you look properly to the water depth of this point cloud, you can see that the real water depth is far away from the water depth that we can get from a structural formation. And this is the refraction that we get from the water. So, of course, we can get some real data with an ADCP linked to an RTK GPS, so we can get real estimates of the water depth using this system. And from these real estimates, we can then make these refraction models in which we can change the water depth that we estimate with a structural conversion to a real water depth. This is the refraction model. And of course, what we are doing now is just is combining 2 different kind of data sets: the raw data set for the dry part of the channel, and this data set that has been converted for the wet part of the channel. Errors in these 2 data sets are different, so that means that these need to be taken into account if we want to go a step further in our investigations, in our research. And this comes the second point that we want to leave on the table that is quite important. That is, sometimes the elevation change in gravel rivers can be very small. It depends on the temporal scale in which we are working. So that means that all these errors, that sometimes are very complicated, need to be taken into account. And that's quite important when we do change detection using this high-resolution topography. This is just a quick example. This is a hybrid depth of difference. So this is comparing to the digital elevation models. This is without taking into account any error in the DEMs. And what we did here is just to calculate the error in each of the digital elevation model that we are comparing. And then we remove all the cells that we consider uncertain. I'm not going further here because there will be a workshop in these gravel bed rivers that you can play with all these techniques. So what we want to show you here is how, by applying an error in the digital elevation model, we removed a lot of cells that are considered uncertain. Yeah, of course, high-resolution topography is still there, and there's still some methodological challenges, and because everything is evolving so quick, every time there are more methodological challenges, and I think that we will never stop. But as we believe that as a community, we have now the opportunity to explore these data sets in a different way, because there are plenty of data sets available at different temporal and spatial scales that can provide a lot of insights on how gravel bed rivers work. Sorry. So let's talk a little bit about the morphological approach, just a brief introduction. So as you know, it's based on the sediment continuity equation. The original approach was early in the 20th century and was was based on the movement of bed forms, estimate sediment discharge by the movement of bed forms, and the application of the morphometric method as Ashmore and Church defined it, implies the repeat measurements of channel topography. Therefore, it's an inverse solution to estimate bed material transport in gravel bed rivers. And in contrast to direct measurements, that they can have a lot of uncertainty, as you know, in terms of the temporal variability, the spatial variability, and so on and so forth. And also in contrast to hydraulically based prediction of sediment transport by equations or by formulas. So for the morphological approach, we define that we need mainly three main data components. Topographic changes, we need to know how the topography changes in our fluvial system. We need a reference sediment flux, and we need a particle or step lengths to close the morphological approach, or to solve the morphological approach. As you can see here, the methods that we can use for each data component, they are variable. So we can choose our method in relation to the objective and in relation to the available information. But if we quick look to the different methods that we pointed here in this slide, you will see that the ones that evolve more, that more advances have, are the ones related to changes in topography. And that's the way that we are trying to see how high-resolution topography can improve the estimates that we can get from the morphological approach. I will come back to this later, but just briefly, I will introduce that to apply the morphological approach, we have two ways. The first is what we call the sediment budgeting, in which we know that the changes in storage in a given ridge are related to the flux coming into the system and the flux coming out of the system. It's a simple budgeting approach. And the second approach that we can use is the step length approach, in which we can estimate a sediment flux in a characteristic landscape using the total volume of erosion in this length of the system and the virtual velocity of the particles. So some examples. There are lots of examples, but I just here we just put some visual examples. People that have applied before the morphological approach. This is based on planary information, so we have areas in which we can draw, we can map the different morphological units. We can calculate the length of each morphological unit, and then we can estimate the changes on topography and the changes on the storage in a given ridge. Then we know an estimate of the bedload flux in a boundary section, in a downstream boundary section. We can solve the different equations that I presented you, and you can estimate the sediment flux. A different way to do it, in this case based on the step length, is using a scour indicator. In this case, it's scour chains. And using the scour chains, we can know the volume of material has been eroded. And then using tracers, this is an example of the movement of tracers, we can know the virtual velocity that we apply. We can apply the step length approach and have an estimate of the sediment flux. Early in the 90s, late in the 70s, Griffiths already applied the morphological approach using cross sections. We have cross sections at different times. We can look at the erosion deposition. We can interpolate different cross sections. And then, if we know a section in which there is a zero flux, or we know an estimate of the travel distance, we can calculate the sediment flux. And more recently, we can use digital terrain models, digital elevation models, and by the digital elevation models, we have the changes on estuarine. And for example, Lane and colleagues, they use a direct sampling in one section to know the sediment coming in too close to solve the morphological approach. This is just some examples with visual references in how they calculate the changes on topography. There is a lot of review going on, and we think that these two papers are very important, in which you can see a nice set of examples and also some reviews of the method. So when you look at the morphological approach, what is clear that instead of direct sampling of bedload transport, with the morphological approach, we are able to link hydraulic processes and the geomorphology of rivers, and that's quite important, how the rivers work and why the rivers evolve in that way. We can look at the mechanisms of shaping fluvial systems, and these are two recent publications in which we do that. And, but one thing is that when you do a literature review and when you look at the proper morphological approach, extracting sediment fluxes, not just the sediment matching in a given ridge, but extracting sediment fluxes from the morphological approach, you can see that it has not been applied a lot, at least what we've seen. And that's, of course, when you back to the fourth Bedload River, Ashmore and Church already review a lot of the limitations, a lot of the constraints that the morphological approach had in terms of the temporal and the spatial resolution and densities of observations. But now probably we are in a stage in which high-resolution topography has improved some of them. So how we can apply high-resolution topography to using the morphological approach? So with high-resolution topography, we are able to create a very nice digital elevation model of a given study, given river ridge. And then we come back later and we can do another digital elevation model. As you can see here, this is the old digital elevation model, and this is the new digital elevation. Then we can subtract them, and we can look at the changes in which we have erosion and we have deposition, and even we can apply a minimum level of detection. We can calculate the errors of each of the DEM, and these errors can be very, very complex. Remember what we discussed about the hybrid approach, combining different data sets. And then we can remove all the cells that are below the minimum level of detection, and we can leave the cells that we believe that are more certain, or they are more certain than the other ones. But of course, with this, what we are getting just is the volume, the total volume of deposition and the total volume of erosion, so the changes on storage. So what we can do just to use this data to have a flux of sediment coming to through the ridge. So we back again to the ways to solve the morphological approach. And the first one is the sediment budgeting one, or sediment continuity approach, as we described before. So we can use the DEMs to extract the changes on the storage. That is this part of the equation. And then what we need is to know an estimate of the flux in and the flux out of a study ridge. We can be very lucky to be in a section in which we know that the transport from that section is zero, for example, downstream from a dam, or in a gravel sand transition. Then that section can be used to back calculate the sediment flux in our study ridge. If not, we can discretize our study ridge in subsections, and then we can have a look to the processes in each one and see if we can calculate a zero transport flux in one of these sections. Using the step length, of course, with the digital elevation models, we can get the volume of material that is eroded in a given time. And then we need an estimate of the virtual velocity, so how far the particles are moving in a given time. And for that, we can use traces, as we see in some of the examples before, or we can get an estimate of the step length of the particles based on the morphology, based on the erosional features that we can look at the DODs, or based on referral pool sequences on bar, or even in the meander wavelengths. There are different approaches to do it. So let's have a look to the case study. Let's have a look to this data set and see how we can get from this high-resolution topography data set. So for that, following the same structure of our talk, we will talk about the sediment budgeting and we will talk about the step length. What we will try to do is using the data set to estimate a sediment flux through the sediment budgeting approach, in which the objective is to calculate changes on the storage of the entire river ridge, and looking in a ridge in which we can say that the output in that ridge of sediment can be considered at zero. In the second approach, what we will do is just use the volumes of erosion extracted from the DODs and then estimate a vertical velocity based on the erosional features that we can see in the DOD to estimate the sediment flux at the flat scale. So, for the first approach, for the sediment budgeting one, this is the data set. I'm sure that you've seen that before in any publications. As you can see here, we did repeat DEX before and after a series of flat events, in total 10 different flat events. As you can see here as well, each flat event has different peaks, so that means that it integrates different flats, and the flat events come from very small, high frequency, low magnitude flat events to low frequency, high magnitude flat events. When you look at the magnitude of these events, you can see that the largest flats, namely the main process is erosion, so the net change in the sediment in the ridge is negative, is erosion. And these flats account the 50% of the erosion of the whole study period. One thing that we did, and it's quite interesting in terms of discussing about the compensation of erosion and sedimentation depending on the temporal scale that we used, is to look at in each cell of the DOD what was the main processes going on in all the flat system. So that means that, for example, these white cells means that nothing happened in the whole flat system. The red cells indicates that only erosion happened, and the blue ones only sedimentation, and the green, that is the most part of the flat plane, indicates that we have erosion and sedimentation. That means that if we don't choose an appropriate temporal scale, we can miss some of these processes. So we are compensating, and that's quite important to take into account when you apply the morphological approach. So for the sediment budget, we have the study reach. You see here the study reach is almost 3 kilometers length. And then what we will do is we discretize this study reach in different subsections. And then from these subsections, of course, the sediment flux coming out from one subsection, from one subreach is the same that comes into the next, comes into the next reach, sorry. And what we assume, we look at one reach in which the changes are almost compensated, coming to one reach in which we have a clear signal of erosion. And we consider that this output of sediment from that reach to the other one is almost zero. We consider zero. That's the minimum flux. So then we back calculate the sediment flux upstream and downstream at the different reaches. So this is the RIS data set. This is the DOD, sorry. This is the DOD, and this is the details of the dates of the DOD and also the duration above a critical discharge during these days. So 8.6 days, the flow was higher than the critical discharge, that it was around 30 cubic meters per second, the one we estimated, and some details of the porosity and so on. So we discretize the study reach in different sub-reaches, and then we calculate the sediment budget in each of the sub-reach. So we have the sediment budget in each reach, and because we apply a minimum level of detection, we can calculate the errors associated to each of the processes, the sedimentation and the erosion. And then we look at one section in which we can consider that the sediment coming out from that section and coming into the next section is going to be considered zero. And is in that section, in which the balance in that section is almost zero, is a little bit positive, but the balance in that section is negative, so we consider that the net flux here is zero. And from that, we can back calculate what is the sediment coming into the system, and then we can do the same in the next sections, and we have the sediment coming out from each of the sections in the downstream direction, and from that we can, knowing the time in which the flow was above the critical discharge, we can calculate the sediment flux in the different subsections of the study reach. So we can look at the longitudinal patterns of the sediment transfers between reaches. We can relate this to the changes on the morphology of the system. We know that this is without having an actually reference sediment flux, but at least it provides a minimum flux through the ridges, and we can look at the spatial variability of this sediment transport through the system. And of course, it could be better if you have a reference flux in one ridge, or if you are downstream from a section that you know actually that sediment transport from that section to downstream is zero. For that reason, it's very important to choose a good design when you have in mind already apply this approach for further investigations. So let's move to the second approach, the path length approach. These are some traditional methods that we use in the risk that we're still investigating, and we want to correlate with the data that we already are now producing. Just traces, painted traces, and we have here the step length, and here we have the RFID mobile system to look at the movement of traces during after flood events. So what we will try to do this. These are results from a PhD from Marco that is around here in the room, and what we will try to do here is that if the patterns of erosion of deposition are telling us something in relation to the path length, and we can use that to calculate a sediment flux, but in this case, flat-based sediment flux average in all the study bridge. So we can look at the erosional features, and we can use the erosional features as the minimum length, the minimum step length during the flood that we want to characterize. And what we do is that we draw the ellipses in these erosional features. We measure the major axis of these ellipses, and then we can weight this axis by the volume of material that has been eroded, and then we can use that to calculate a virtual velocity and apply the morphological approach. So here is some results of the 10 different floods that I explained you before with the length of this, the mean major axis length of these ellipses. And then we can start looking at the relationship between this data with any signal of flow magnitude. This is in this case, this is just preliminary results. It's an integration of the flow above a critical value. The critical value is the same that the first example that I show you. And then we can have this relationship between flow strength, flow magnitude, and volumetric sediment flux. So what are some of the remaining challenges and opportunities? So of course, temporal scales have improved, and now with new technologies, we are able to get repeat topography very, very quickly, and also we can extend the spatial scales of this topography. But our question is, do we still missing important processes? Are topographical change, even if we are able to work at the flat scale, are topographical change temporally integrated to too long periods to understand the processes that reshape alluvial channels? And that's an example of one we want to say. We are able to get topography and roughness and so on and so forth just before the floods and after the floods. But what's going on during the floods? What's going on under the water during the floods when we are not able to get much topography? We use that cartoon that has been well known, the cows cartoon. We are able to see the cows in this condition with low flow condition, but what's going on during the flood? Well, we're missing some information that is very important in terms of compensation and in terms of bed mobility and so on and so forth. So yes, we improve a lot, and that's an example that Richard Williams and colleagues recently published by integrating ADCP measurements, bed velocity measurements, RTK GPS, and TLS during variable flow conditions in the reefs as well. So this is the diagram. I will not go further here. But what we do in this case is we link bed mobility, topographic change, and changes in morphology on the different flow conditions, and we look at the mechanisms of changing this part of the river. So yes, we may get some insights of what the cows are doing here in this cartoon, but is the technology available for large scales? This is for small spatial scales, but what's going on when we talk about a rich scale? So the second point that we want to put on the table is that we need consistent high-quality surveys. We need network controls to estimate the errors, and when we integrate all these data sets, these are quite important to know that what we get is the most accurate that we can get. We need to integrate methods, as we have seen briefly in this presentation. And for example, for the zero flux assumption, for example, it's very important to make effective study designs before we start collecting the data, and that could be quite important. And of course, all these technologies require some training to decrease as much as we can the errors. So finally, we need to scale these high-resolution topography methods to enable to look at the source, to see morphometric analysis, to quantify, of course, storage, the transmission and the position reaches, and link this to particular fluvial style. So this is not a way without a great team, but with the great team show the way to the Tableau of USA. And I would say many thanks to everyone that has been involved in these different projects, people from different research groups, and also the RISCAM team, that is a very, very long team of people working and collaborating together. So this is also all the funding that we have received to do this research, and that's all. Thank you. Thank you very much.
Thank you very much. We'd like to invite the second speaker, Marwan.
Thank you. Thank you. It's a great opportunity to be finally in Japan. I would like to start by basically wishing those who celebrate the Jewish New Year, Happy New Year. It's today, the New Year, Shana Tova. And I would like to start with a little bit of history and to talk about something that happened in 1870. 1870, France declared war on Prussia, which is part of Germany today. And after a few weeks, the Prussian army lay siege to the city of Paris. And it was very difficult to communicate with the city. Engineers and officials in the government of France tried to find ways to communicate, and they came with the idea that they should use the river. And the way that they decided to use the river is to build a small poles about 30 centimeters each, to fill them with the mail, to drop them about 2 kilometers upstream, and to let them go through the city. And 6 or 7 post workers will stand somewhere with a net, catch them, and this is the way to deliver the mail to the city. They dropped 55 poles 2 kilometers upstream of the city. 2 of them, they were discovered 35 days, about 170 kilometers down, far away from the place that they started with, which is about 5 kilometers per day. Then over the next 15, 16 years, they found another 17, and in 1982 they found another one, which found in total about 20 out of 55. The issue here is that what the city did after that, or the French government, they gave medal to the 6 post workers who did not catch a single pole in the river, so it did not help. And they fired all of the other engineers who were involved in the project, and they lost 150,000 francs. In that time, it's a lot of money. So when we start working on sediment transport using a tracer, this was the reality, finding about 20–30%, and try to make a story out of it, or to try to study or to see how the sediment move in streams. My hope is now that we are a little bit better, and we are, in terms of technology, and we know a little bit more about rivers. So what I'm going to do today is to talk about something that many people already described in detail. So there is no need to go through the way that sediment move through streams. It's individual grains that move. We need to understand how this process works. We need to develop techniques in order to study not only the movement of these stones, but the interaction between the channel, which is very complex kind of boundary with the channel morphology in the top of it, and the flow conditions. All of it at the same in order to predict and in order to help solve practical problems. So all of the tracer study is an intermediate kind of area in between most of the method that we have been used, which can help us learn a little bit about the channel morphology and the sediment transport. So one can think about it an easy way, like the 55 poles that the French tried to throw into the river. One can throw a few stones and follow them and get a little bit of statistics. But over the year, what it proved that getting this statistics very hard. And this is really limited our ability to interpret it and to use the data that we get from the field. And one of the difficulty has to do with the technology that we use. Although we have a lot of better technology today, but still we are not in the situation that we can take a large sample of grains and trace it and follow it and get detailed information on how it moves and to use it in order to interpret sediment and channel morphology. So what I'm going to do today is to look on the movement of the grains, and I'm going to focus really on the geomorphic scale, and I'm going to take you to the field. So basically I'm going to tell you what I'm doing these days rather than what I did a few months ago. And I'm going to use that in order to link between what was said in the morning in the lab or in the theory with what happens in the field. I will, as I said, look on the complex nature between the channel morphology and the sediment that move in the rivers, and I'll be looking onto a temporal and spatial scales. But also I would like you to know that I'm going to work on something that called the geomorphic range or the geomorphic scale, which means that it span a few or at least one complex event, which doesn't follow the simple description of the spatial and temporal way that sediment move. And in order to do that, I'm going to use only data from two case study, and I intentionally choose these because I know about them. This is the first thing. But the stream that you see in front of you, it's in British Columbia. It's a diverse kind of a channel morphology. It starts in the upper part with a rapid, which is Plamped in Montgomery, Peffington terminology, into a refill pool. And this is actually continue downstream into another refill pool and then another step pool before it's entered to a larger river system. The unique things in it is that we know the input of sediment into the system, we have traps and so on. We know the sediment that leave the system because also we have traps, and we have also traps in the end of each channel morphology. All of the morphologies experience the same kind of flow conditions. We have at least 1,500 tracers that we insert into the channel about 12 years ago. And as I said, we have different kind of methods to use. So it's a long kind of term data set that can help us learn a little bit about the interaction between the channel and the sediment transport. The second case study that I will use here briefly is the Half a Moon Creek, and again another case study with about 1,000 tracers. It's ongoing study, diverse channel morphology. As you can see, it starts from what Nate called it a transfer kind of a reach into a meandering channel bars and so on into another transfer reach and so on. So it's kind of complex channel morphology. This stream experienced one flood, its snow melt fit system. I will be using 5 years of data, but we are going also to look into more data in the coming few years. Okay, so Nikura suggested to look on the spatial and the temporal motion of a grain in terms of three kind of scales. One is the local, which is between two collisions. One is the intermediate, which is between two step length or between two rests, and what the global, which a scale that include a few intermediate cases. We heard quite a lot of discussion around or research about these kind of local intermediate scales, but I would like to look onto the global scale that Nikura defined in a little bit different way, and I would like to look on it in terms of geomorphic. It could be as a part of the global scale, but it could be in its own as a different scale. And this scale, when we have a lot of grains that they do not participate in the movement, they could be on the surface, they could be underneath the surface, but they do not participate in the movement, although we have the condition or the flow competence to mobilize them. And the importance of these stones has to do with the sedimentary units and the channel morphology that we deal with it. So if we are going to look onto the channel morphology, we need to pay attention to those that often move, make the channel morphology the way that we see it. So if you think about it in terms of, and the diagram that you see in the upper one there, it's just two kind of cases, one 2006-07 floods and one 8-10 floods, no floods in 2009 in this case. And you see quite a mosaic or a colorful, smartest kind of a picture of the surface. In the upper one, most of the particles are in green. That means they moved. We did not recover, and if you actually remain in their place, and some of these, if you they remain in their place, they were found on the surface and in the subsurface. The next year, we have much more remain in the surface, which constitute what we called actually in one of these places as a lateral path. And if we look on the years or in the magnitude of the events that we trace, then some years we have a large events, as you will see later on, that scour the whole almost depth of the scour layer or the layer that we have the tracers in it, and most would be mobilized. Some years we have events that they scour much less, so the deeper one will remain there in residence time for a long time, which will dictate their travel distance for the years to come. And if we take the last one, we have, in that case, is a small event that limited to the upper layer, and with it the movement of the sediment. And if we look in it in terms of residence time, these two cases, the Aldub Hague is in Scotland, and East Creek, what you see that is a large proportion of the particles remain in a place for a long period of time. Residence time of 200 hours in East Creek, it's equivalent of 2 years. So there is a quite long period of time that the particles remain in a place, and therefore the waiting time or the residence time, not just the rest period in between steps, is very important to think about it. Again, if we look on the Aldub Hague, it reached up to 600 hours, which is a significant time again. So for this reason, it's important for us to think about the geomorphic range and the mobile and immobile particles when we think about the evolution of the bed surface. So my concentration or my focus is going to be on this for the rest of the talk. Okay, so I will look on the particle mobility at first and a little bit in relation to the channel morphology. And in this case, I want to utilize the large data set and the small nature of the stream that we deal with it. This is for us a second flume. It's practically flume because we can, if we want, control the input. Because we have a trap upstream, we could control the input to the system and change the feed conditions or increase the feed if we ask for permission to input sediment into the system. So it's a kind of control system, well-defined banks, as you can see here, and it gives us the large number of traces that we use. It gives us to look on the spatial and the temporal pattern of particle mobility in the stream. The same in the case of half moon. Half moon, a case study with a large data set. And if I start from the first diagram up there, you can see this is the time that we introduce the tracer into the channel. Most of them remain within the first region, which is the transfer zone here. The flood was small, as you can see here. And one can conclude, in spite of the fact that the particles were artificial in the surface, they did not move beyond the channel morphology that they were introduced to. The next event was large, as you can see here, and most of them remain within the same morphology, but quite a few move into the other morphologies, meandering 1, meandering 2, and transfer zone, and so on. Later, another small event, most of the particles, color-coded, move within channel morphologies, as you can see here, and so on. So what we see here, if we look on large event, then the particles move well beyond the channel morphologies that they were in, which means that the movement spanned more than one channel morphology. And again, you can see here. So what we see here in this case, it is certain pattern, and during small events, most of the movement remain within the same channel morphology, while in large events, it could move beyond that. And if we look on the cumulative distance of movement for the traces over time, this is the particles here, and this is the distance. And you see the majority remain in the area that they got installed in it, which is the transfer zone. But we have a second peak in the first part, we have a third peak in the second part, and we have another small peak here. If we scale our data based on the spacing of the parts, as we heard before that the spacing is very important for the estimation of sediment transport, then what we see in small events below bank-foot discharge in this case, the particles move within the same morphology, which means that the maximum possible movement in this case is between parts, or this is the kind of distance that you need to think about if you want to estimate sediment. Again, the event that you see here. While in the case of large events, you need to think beyond parts, and of course it depends on the number of stones that we use. The larger the number, the more accurate we estimate. So the main conclusion here is that the channel morphology matters in a way that actually trap sediment, store it, the sediment move within that channel morphology until a large event comes and mobilize it further downstreams. And if one can consider the frequency magnitude of flood, then quite a lot of the event, they will mobilize the sediment very little, which is within the same channel morphology. If we look at this in detail and we look on two different kinds of reaches, one here, a rabbit, and what we did here, we took the whole channel and we kind of put a grid or cells on each channel here, and we look on it the same way that Wilcock suggested in terms of partial, no mobility, partial mobility, and full mobility. We use the same definition, and what we did here, we look on the mobility for each cell in itself. And we look here on the unit scale, which means that roughly we are looking on one or so riffle pool system, a little bit longer. What we see in the 0.4 kind of half bankful discharge here, quite a lot of the rapid channel remain with either partial mobility or no mobility. If you look carefully, there are a lot of stones grid, which means they did not move. And very few of them experience full mobility, and they were located, as you can see, in certain places. As the flow increases, more cells experience full mobility conditions, but still quite a lot with partial or no mobility. And even under the condition of 1.5 bankful discharge, still we have a lot of the channel experience either partial mobility or no mobility. There are here these cells with no mobility, as we see. So in this case condition that we are looking on it, even under the condition of well beyond bankful discharge, part of the bed shows either partial mobility or no mobility. If we look in the riffle pool, which is immediately downstream as a reach, What we see the same trend roughly in this case. We have the same kind of partial mobility extended to wider areas, increase in the mobility, and a significant increase at higher flows. But you see also most of the mobile cells are located in this area in the middle. We try to use correlation and so on to see if there is any correlation. It wasn't successful. But what we did here, we decided to see if there is a correlation between the topography, a change on the surface, by looking on the topography or the scour fill in the channel and the shear stress distribution along the channel. And this is what we did. This is just a case. Again, this is the map that we used before. These are the full mobility kind of cells that we have. This is the topography of the channel. These are the high areas with the low areas. And what we have here, a detailed map of the net change in the channel in terms of the scour and fill. And you can see quite a large area of the channel experience zero change over the floods, but in other areas either experience erosion or deposition. And if we look on the shear stress, then the highest values of the shear stress are located in this area here, in the middle area here, and this here, which is roughly fit the distribution of the mobility of the material within the channel. This is on the scale of the riffle pool that we dealt with it. When we work in it on the cell scale, we couldn't find any significant correlation, which shows the stochastic nature of the sediment mobility. Sorry. Okay, so what we did here, we decided to take this a further step and to look on all of the flood, because what I showed you a few of them, and to look on all of that, we decided to look on each cells and to summarize. And what you see here, these are the cells that we experience no mobility most of the time, significant increase in the mobility, and in much larger event, a lot of the particles move. Again, in the riffle, this is looking on it in terms of cell by cell, looking on it in terms of channel morphology. The most interesting part here is that the lack of a change after a certain value in terms of the mobility in the pool. All of our results for all of them here, if we look on them in different ways, we end up in the same kind of situation, whereas the riffles continue increasing a trend in terms of the mobility. If we look on it as a whole reach, there are quite a lot of similarities, but in most cases we have, in all of the flows conditions, we have a situation that we have even the highest conditions, no mobility. If we look on it in a little bit simpler way, then we have the relative mobility here, and we look on the whole reach. What we were surprised that really we do not see any major decline in the mobility with the particle size. There are a little bit here irregularities in the plots, as you can see here, but in overall there is a little bit decline here, there is a little bit decline here, but it's not that clear. And as we reach the highest flows, all of the particles are equally mobile at the same thing, which is almost 90%. And see the same trend in the riffle pool. If we consider the distance of movement in this case, then in low flows, as you can see here, we have a sharp decline in the mobility or in the travel distance with particle size. As we move to a larger event, there is increase in the mobility with particle size. These kind of crafts, these are very exposed, so they are highly mobile, and these are too large to mobilize, so there is a decline. But in very high flows, all of them move at about the same kind of distance. If we want to look at it in terms of exceedance probabilities and so on, I did not try to plot any curve here, but if you think about it in terms of high flows, this is the difference between the rapid and the riffle pool in terms of the distribution. In low flows, they are roughly on the top of each other. In high flows, they depart from each other. And if we go back to the idea of mobile, immobile, I would like to look on the issue with the burial depth and to see what we can learn from the burial depth, because some of the techniques that we use do not provide information on burial depth. And I want to emphasize the importance, because we look on the mobility between buried and not buried in order to see how the process works. So if we look on the fractionally grained buried here in this case, there is a clear trend of decline in burial depth with particle size for almost all of the flows that we consider. This is 0.4 Bankford, this is 0.8, and the other, but one. The large measure event that we had, which is 2.4 Bankford discharge, mobilized all of the particles 100% and actually end up in all of them buried. 2 events after that, the same proportion appeared on the surface, which means that the system kind of became in equilibrium. If we look on it in terms of mean burial depth and the grain size, we can see a major decline in the mean burial depth with the grain size. But the most important thing here, which is related to other talks and to modeling and so on, is related to the assumption that the scour layer or the active layer or the mobile layer, it's about 2D90. In our case study, in most of the cases, it's between 0.3 to 1D90, which is quite low, and it probably has to do with the structuring on the surface and the nature of the river itself. And again, burial depth matters quite a lot, because if we think about probability of sediment mobilization, and these again 2 creeks, and you can see that many of the deep particles remain in their place for quite some time, and this is very important for the bed surface evolution. If we consider again the same kind of situation and look on it in terms of depth of layer, then you can see that the low event, the depth of active layer decline if we use the burial depth, but during high flows they are equally, the depth is the same for all of them, or the activity. Okay, so we suggested in the past a certain practical relation. Recently, new practical relations have been developed for the estimation of sediment transport. These are just 2 examples from the ones that has been in the literature. There are others. And the issue here, which is very important, that when we start trying to summarize the information on the topic, we try to update or to try to test these kind of figures or models or, relation or others. But we couldn't get information in order to do that, and we had to abandon the idea. It's really important when we report on these kind of tracer studies, we report the same kind of information, so any new idea can utilize whatever collected, published, in order to test new ideas. So we end up in trying to test our old kind of relation in terms of distance of movement and axis stream power, and we try to stratify data based on channel morphology. And the step pool morphology plot a little bit low here versus the riffle pool in the middle here, and gravels over sand somewhere here. But it also, you see, a quite very wide range of results for the same morphology, which partly has to do with the quality of the data and the information that we have. So sometimes if we really have make an effort and describe our case study in much better way, it could help maybe clean some of these relations. The other relation, which I was very surprised to see that it survived a little bit more than the one before, it has to do with the scale particle size with the scale distance. Although there are some data kind of plot below here far away, but most of the data still within the errors of the relation, even those from step pool morphology that they were declared out of the range. When we plot them, they fall in the same range. But this relation, or similar to this relation, this relation or the relation before, or similar to the relation before, are important for the estimation of sediment transport in stream. So I would like to summarize by saying that we still need improvement in the technology, and either in new technology or improve the technology that we have. We heard and we will hear more about more successful new technologies, hopefully. But it also, we need the technology that provide detailed information. The mapping and looking on the temporal and spatial scale of mobility was possible because of the large number of particles that we use. Otherwise, we couldn't do that. We still think that a lot of work has been done in the local intermediate scale, and we are learning quite a lot on this topic. Some of our early work can be classified around the global scale, and others which related to whatever kind of distribution, exponential or gamma distribution. Most of our field studies are done in most cases on the geomorphic scale, but it's really the interaction with the channel morphology the focus should be in this case. Long-term monitoring station needed. We kept financing this research for the last 12 years using different sources. It's impossible so to continue from a regular research grant. Maybe this is a topic that government agencies should look into it, because to study the importance of the sequences of the event, the channel morphology, the input of the sediment, need a long monitoring station. Channel morphology matters a lot. Magnetic view of events and so on matters a lot, as we heard before and we will hear later on. Bed mobility even at high flow conditions is still sporadic, localized, and we find places with no movement even when the flow well beyond the bankful discharge. Burial depth is important. There are a few nice studies, Carnation Creek, one of them, East Creek and Aldobheg, but we need more studies like this. It's very difficult, very hard work to do this, and we disturb the bed, which is a factor that we need to consider, but still we need to make an effort in this case. The immobile particles, or the depth of the active layer that include both mobile and immobile, it's important for channel evolution, channel morphology, and important for the residence time. And that's it. Thank you.
Okay, we are now open for questions and the comments. Before questioning, please use the microphone and identify yourself. Yes, please. Helmut? Two speakers, please come to the platform.
Helmut Habersack, Book University, Vienna, Austria. I enjoyed very much both talks. I think they were very exciting for me to see. I have two questions. The first one concerning Damia. You showed us in one diagram the elliptic determination of the step length, I think, if I understood it correctly. Maybe you could explain more of it, because
The last slide.
with the elliptic determination of the... Yeah. I was just wondering whether you used additionally also the tracer information to combine this. Okay, that answers already my question. And for Wawan, I have the question concerning the depth, the burial depth. I think also it's very important to have more information on the vertical sorting processes and numerical models which we use. They try to have several layers. Now, maybe I misunderstood, but did you say that maybe the burial depth in your stream here was about 0.5 to 1 times the grain diameter or something? So it was a few D90, so it can be about 10 centimeters or something. would you think that is already a layer, because maybe it's even the top layer or the armoring layer that you are looking at, or is one stone covering, or that was not?
It's about 15. If you think about the D90, the D90 is about 12, 13 centimeters. So this is roughly, yeah, a little bit more than 10 centimeters, and that's brief. Yeah. This is the depth of we have burial depth a little bit deeper, but these are the average values. When we look on it by looking in all of the sizes, you can see that there is a decline with particle size. So when you average all of them, we get about 12 centimeters, something like that. Now, I did calculation for the depth of the active layers in Aldov Hague, and I got more than that. So for our case study, this is what we have. All of the assumption always that 2D90 provoke me to put this number, that some system they don't work that way. That's all. Yeah.
Okay, thank you.
Yep. Back row.
Philippe Belludi, University of Grenoble, France. A question for Damien. In the Reese hydrograph, you get the chance of having quite frequent leveling, but the result is that these levelings are not completely at low flow. So you will get some uncertainties because of the water level and the submergence of the areas, right? So what would be the global uncertainty due to these different flooding positions?
So, I mean, you're talking about the topography that we get?
I mean that the water level has changed. So what you get from your leveling depends on is there water or not. And if at picture I there was water and picture I+1 there was not water, so you get some uncertainty on this zone. So as you push the results from one section to the other, you accumulate the errors. How much is it as an error? Thank you.
Dave Milan at University of Hull. Question for Damir. Enjoyed the talk there. The tracing that you're doing with the pit tags, I was wondering, you're using that to work out sediment flux. Had you thought about how you can get a size, a competence duration based upon different grain sizes, and how are you actually doing that?
Yeah, to be honest, we didn't look at properly this data set yet. So we are looking at the data set, so we didn't do it. The big answer is yes, that's a good point. So I put the tracer, the pictures there, just like an example of we got this data. We're going to use this data to look at the results we could pick up from the different two approaches that they took here. But this is just a preliminary class, and we can look probably the tracer data. But yeah, it's kind of a big answer we can really look at data.
Okay. Yep.
Peter Nelson, Colorado State University. I have a question for Marwan, and this relates to the morning's talks. I'm curious if, in all of your tracer data, if you have tried to quantify or characterize the conditions under which these particles are distrained, in terms of maybe the shear stress at the end of the event or the local grain size distribution at the location of deposition or distrainment?
It's quite an important question because it's related to what I said, and maybe it will give me opportunity to repeat in different way. I feel that we work in two different kind of scale in terms of these tracers, and the middle point, which is really very important. This is the situation when we have the surface arrangement, the local conditions of the particles, the entrainment conditions, or the sedimentological conditions of the particles, and this is one of the difficult things still. We can do that. We did not do that, but we can do that. We just look on relative mobility at this stage. But it's possible for us to characterize the location beyond just if it's a poor refill. Yes, that's a good idea.
Anyone? Yep, below. Did you? Yep, below.
Oh, sorry. Okay, two questions, two people. Marwan, can you put the slide back up that went by kind of fast where you had lots of pretty dots? That. You've divided it arid. You didn't really give us an explanation. You showed this and moved on. What is this telling us about movement, morphology, and aridity? I mean, that was one of your categories, you see.
What we tried in the past to do is to try to relate the mean travel distance to the axis stream power. There are a lot of arguments which are good that you cannot just use the peak flow in order to characterize the flow. You need also to think about the time that available for movement, which is the duration. So this is a simple way of looking in reality, assuming that the particle is moving at or close to the peak flow. What I tried by plotting this is to see if there is a stratification based on channel morphology. And I saw that sometimes there is a stratification. This is the Step Pool river in the Italian Alps, then Cordon, what is the name of that? Anyway, but the other one was up there. So I do not think this is a kind of successful way of classifying the travel distance using this channel morphology. And one of the reasons when I went and I started saying why that Step Pool stream is located so high, I did not have enough information or the history in order to see or to explain it. And my point here is that we need to look into the integrated stream power, faults, or shear stress, or whatever. This is true where this is more to simplification. But the other issue is that most of our data are in this kind of frames that we cannot use them or we don't have the information. That's all my point.
Okay.
I do not advocate this over the
Okay.
other.
And then my second question is about the morphometric surveying. And you said you need a mixture of methods, but have you explored the use of bathymetric LiDAR?
Yeah, you have LiDAR.
Right. So I was wondering whether you've tried it and didn't find it was satisfactory, or...
No, we
Okay.
we don't have well, we're working now. We have this kind of
Right.
with this kind of LiDAR showing the size of the spot of the laser, sometimes it's quite big, so then we are doing even more LiDAR.
The new Titan system has much smaller dots.
Yeah, that's what I say, that the methods are going
Yeah.
too fast. But
Okay.
I'm sure that they are. That's an option. And then you have a single data set.
Right.
And you can calculate it and propagate there.
Okay.
Yep.
John Larone, Ben Gurion University. thank you both. Very interesting talks. I'll start with a question to Damia and then maybe a comment to Marwan if you wish to answer. So, Damia, you talked to us about the areas in the bed that you managed to identify where there is movement. Now, there are some areas where you do not identify movement, DOD 0. Those are very interesting, sometimes even in between large events. So my question is, have you tried to look into that in order to identify whether they have some particularities and what part of the riverbed they are, etc.?
No, that's a good point. We did it. Because this guy was looking for me to see the roughness, and see, for example, the lake watching the roughness, things that we do. But we only know in that part that the changes to the activity is uncertain, and we can say that it's a real change. Of course, if we remove the uncertainty and all this, for sure, we will have a lot of observations and nutrition that we will know if this power is real. But yeah, that's what we're going to look at this part.
Because those areas of the bed where you assume that there's been no, or you cannot really say how much movement there was, there are other instances. For instance, if you take a hill slope or a first order basin or whatever, zero order, and you want to know what changes have taken place there, erosional, depositional, by actually measuring physically what comes out and then using a DOD, you can say something about those areas about which you can't really say anything in the depth of difference, and it can be a very interesting part of the total area.
Yeah, and also, even if we can analyze the project very quickly, because we have all these networks and all these DODs and so on and so forth, we don't know what's going on within the plant, so we decided that we like now the DOD. So the evidence integration and achieve that concept. So that was on the last slides. Yeah, because we can get the next working before and after, and also now we can work at the scale of 30 kilometers or 20 kilometers much larger than before. But what's going on in the past? So the change, the work is going down and up as well, and we don't know about that. So I have this process of involving some of the approaches that we look at the end of the flight. So this is still some open questions that we some work with which are the other sources in the region in different conditions, and they limit the mobility and changes of the geography with technology. But yeah, of course, we are concentrating on small specials, but also not in the larger specials. So is that, yeah, still a lot to do with this problem.
Thank you. And the question or comment to Marwan. We heard today in the morning a paper that some of you may have read by Tsakiris and Papanikolaou. Have you tried, Marwan, or will you try to identify the depth of burial without really disturbing the bed? Because in some conditions, actually disturbing the bed affects the results. Have you considered it, or have you started using that?
Well, thank you. You actually pointed out that paper to me when I was revising my paper, and I used it. It's something to consider. Yes, we are planning to do new tracers, so this is something that we will consider, and we will talk to Tanous about it. Yeah.
Thank you.
Gordon.
Gordon Grant. Marwan, you give us some, well, both of you have given us some really beautiful images to think about in terms of how particles move during events. Yet I find myself wondering about that I think we're all still stuck a bit in thinking of transport as some sort of steady, uniform flow phenomenon, whereas we all deeply understand that it is not. It is unsteady and it is non-uniform. So even if you take this image here, Marwan, where we do the typical thing of we say, here's where the particle started, here was the magnitude of the flood, here's where it ended up, and we try to make sense of that. And yet what is really happening is that there is some initial erosional episode which occurs at some piece of a flood hydrograph. That particle is then being transported through fields, force fields that vary spatially as they move from unit and geomorphic setting to geomorphic setting, and then it is deposited perhaps at a different point in that in that time scale of the flood and in that force, and then repeated. So I'm just wondering, how do we make that next leap to developing a much more dynamic view of particle transport as it occurs at the flood scale? It seems to me that we have the technology to actually put, timestamps on things and actually track our particles, not in this sort of static sense, but in a dynamic sense of a changing fluid field. I'm just interested in your comment.
So actually, I was hoping that you are sleeping and you want to ask a question, but it did not work. We know each other. You are right. I think it has to do with technology. I think we have some insight, especially when we are thinking about a few grains, we can follow them and we can see their movement. The question, what can be done with the few stones? And this is why I said that the statistics is hard. It's hard in a way that you get very large number in a way to look on the spatial and the temporal better. So I'm hoping that technology will help in this, and there are new technologies. I started by talking about 1870, and that they threw the metal balls and they recovered only 40. This is what we used to do in the 50s and so on. So we are now better, but hoping that we will have better technology. Yes, I agree with you.
Yes, second row.
Colin Thorne, University of Nottingham. Again, two questions. Marwan, looking at some of your earlier diagrams, I thought I could see a spatial correlation between mobility of particles, the green and the red dots, and the wood in this channel. We heard this morning about the huge importance of boulders as large roughness elements. Well, the kind of big logs that are in your stream there are much bigger than boulders. Do you feel they exert a strong influence?
They do. Actually, we did another study in that place, and we noticed is that two things. One is that the wood play a role, and a significant role, especially downstream from the place that we work, like that I showed, more than the place. And in certain places, we were kind of puzzled if to remove a larger tree fall in the middle of the study, if to remove it or not. Yeah. And we have to battle also with beavers and so on. Yes. So that's true. But the other thing that what we notice is that the areas that they scour in one event, they experience a deposition in the other events, which others describe it, and you can see it as it goes downstream. And upstream areas experience scours early in the season. As we go through the seasons, more and more downstream than upstream. And our traps actually show high values in the upper part early in the season, very low values in the lower part, the opposite later. Yes.
And with respect to the Reese River, I had the privilege of examining Richard Williams' PhD thesis at Aberystwyth, so I was able to drill into the Reese data set through that process. It strikes me when I look at the maps of change, the DODs, and the red and the blue, that red and blue doesn't always mean the same thing, because sometimes erosion could be bed scour, a vertical change, and sometimes it can be bank erosion, a lateral change. And I wonder, do you ever think about maybe using red, orange, blue and green, and starting to look at morphological adjustments in the horizontal plane and the vertical plane. I think they're quite different.
We can use the aerials to map the different morphology of the river and trying to map, as you say, changing the colors. But no, we didn't think about that. But you are right. Yeah, in the Rees is a very shallow river, so some of the processes are changes of erosion, but some of them are related to bank erosion in the past. Yeah.
So
Some
morphologically
local processes.
different things.
Yeah,
They're not red or blue.
Yeah. Thanks.
Okay.
Francesco Comiti, University of Bolzano, Italy, Formula 1. Looking at this graph, so do you observe a stratification also if you plot the virtual velocity? So did you try to not just stay within the distance, but to account for the duration and see whether the virtual velocity also differs based on the morphology?
We did not do that because some of the data here, we only have the maximum discharge and or the depth which of the water, so we could calculate things. So many of these we do not have the information in order to do that. We did this for half moon, and you can see this is energy, whatever here, variability, just a scale for the flow. And you can get less kind of scatter in the data, but it's still, this is one stream, but the change in the morphology quite amazing from transfer zone with barely any storage area, which means that most of the, and annually the sediment move through the system as we move downstream bars and so on, so which is not different than this kind of relation or other relation that has been suggested in the literature in the last few years. So yes, we should do that. We did not.
Okay, last discussion.
Murray Hicks from NIWA in New Zealand. Question for Damia. I guess I was slightly uncomfortable with the use of the length of the erosion zones as the measure of the step length, and Helmut's asked the obvious question about checking it out with tracer. And I guess in following on from Colin's comment about Richard's modelling, the other way to validate it would be with injecting synthetic tracer, if you like, into the morphological model, and checking it out that way. Are there plans to do that? Yeah, I reckon it'd be a good thing to do. Thank you.
Thank you very much. Before closing the session, Damia, you have something to announce? No? Joe, okay.
So, if you're registered, if you're a postdoc or a grad student, you're registered for the workshop or short course on Saturday morning. Come see me. We have everything ready for you, but we need to make sure that you get set up so that we're ready for that workshop. Just find me at some point before Saturday morning.
Well, thank you very much. Thank you very much for the speakers and discussion. Thank you very much. Now we have a coffee break, and you are requested to be back the 4 p.m. sharp. Thank you.